Okay, so in science and lab, we have two types of data. Again, the first one you are very familiar with because this is what you do when you go to lab anyway. Okay, and the first one is called a quantitative data. Quantitative data. Quantitative, quantity. And this data is what you measure. So measured values. So we measure mass. So maybe we have 5.010 grams. So this is a measurement. So we have a number and a unit. So we measure mass. Volume is a common measured value. So maybe we have 15.55 milliliters. Use milliliters for units for volume. Temperature, Celsius, most time for us. Any others measurements that you think we might use? Not so much length in class. Maybe more in physics you would use length. Mass, volume, temperature, that's usually what we use. Okay, so measured values, so it's a measurement is a number plus a unit, and these are some examples. So temperature, maybe it's 21.6 degrees Celsius. Okay, so this is what you're used to. You're used to getting into lab, you record down what you measure. Okay, so that's what you're used to doing. It's called quantitative data. Now your data should be in a data table. So anything that you record, you're going to devise into a table of some format. Okay, your table should make sense. Right? You have titles at the top, so maybe we have a table like this. We put substance in this column. We put mass over here. Put volume over here. So substance 1 has a certain mass, certain volume. Substance 2, a certain mass, a certain volume. So for a table, you have headings, right, at the top of every column of what you're measuring, of what you measured with your data. Right. We'll spend some time kind of working through that a little bit. But for today, do we understand what quantitative data is? Okay, it's things that you measure. Okay. The other type of data that you may not be familiar with is called qualitative data. Qualitative data. And qualitative data is your observations. Okay, your observations. And your observations are going to be based upon your senses, right? Your senses. So what's probably the main sense that we use on a daily basis? Yeah, sight. Very good. So when you get into a lab, you're going to observe what you see. Okay, not only with the equipment that you use and the chemicals that you use, but also the process. So if Carter and I were partners and we spilt some solid mass and transferring something, that would be as a visual observation. We spilt mass, or we dropped, or we broke something. Okay. The other sight might be what you actually see during the chemical reaction. Maybe you have a white powder that you start with, so you're going to describe that white powder. Okay, or maybe it's blue, maybe it's pink. And then you're going to describe what you see during the process. Okay. Now, when we do these observations, we want you to be detailed or specific when with your observations, within a reason. You don't overkill it, okay? Don't overkill your detail with that. But when I read your observations, I want to experience what you experience. So when I read this, I should see, or I should experience what you're trying to communicate with me, all right? Now, my example for that would be this. If I said that a blue solution was created, okay, imagine that. A blue solution was created. All right, you got a good visual? Okay. Now, do you see a problem with that? What's the problem you're thinking? Yeah. So when I say a blue solution, you're probably going to think of your favorite color, or a color that you've seen recently. What were you thinking? Blue from up there? Like right here? That kind of blue? Okay. What were you thinking? More of that blue. More of this blue? Okay. You have a different blue? What? Like a darker blue? I was thinking midnight blue. That's kind of my favorite color. Okay. So that's the problem with that. So we want you to be detailed enough with your observations so that we can experience the same thing. So was it a teal blue or aqua blue or like a dilute blue or Kool-Aid blue or something like a chartreuse? All right, guys don't know what that is. Girls, chartreuse. Okay, country blue, sky blue. Guys, it's blue, red, green, right? Girls, you have different shades of everything. Okay, all right, we're good. Okay, so that's probably the main one that we look at. Okay, give me another sense that we use. Touch. Okay, touch. So what can we kind of feel? So it could be hot, cold. Look at texture. So is it jagged? Is it sharp? Is it rough? Is it smooth? Soft? And if you want, you can make some comparisons. Feels like flour. Okay, so flour has that very soft, powdery type of texture to it. Okay, so that would be touch. Good. And if you want to do a comparison to something more common, you can do that. Like feel like sandpaper. Okay, that's a comparison that we can get a good indication of what your observation was. Okay, give me another observation or another sense. Okay, smell. When we do the smell, we want to use a wafting technique. Not waffling, wafting, not waffles. Wafting technique. And is anyone familiar with the wafting technique?
Is that where you kind of wave your hand to like get the fumes like come over to you?
Yes, very good. So if this was a test tube, and there's a reaction in the test tube, and there's vapor coming out of the test tube, I'm going to waft it. I'm going to take my hand and I'm going to kind of waft or push the vapor toward my nose, and I can take a smell. Okay. You do not want to put the test tube under your nose and take a big whiff. Do not want to do that. Okay. Reason being, let's say that you're producing ammonia. You take a big old whiff of that. Okay. It probably will open up your sinuses, make your eyes water, and it could knock you out. We don't want to have that happen. Okay. If it's a very potent bad smell like butyric acid is the worst smell almost ever you can imagine. Soccer cleats, who are my soccer people? All right, reek out the house. Soccer cleats, hockey gloves, bad smell. Okay, butyric acid is kind of like that. Right? You don't want to take a big whiff of that. Okay, so for safety caution, guys, we're going to use a wafting technique. All right, give me another one, another sense. Sight, touch, smell, hearing. Good. Okay, so we might have crackling, fizzing, whistling. Okay, we have different sounds, the chemical reactions. And any others? Taste. And that's a no-no. no, we do not want to taste things in lab. And Kim B will make ice cream. You can taste that. Okay, you can taste that. But hey, look, that white stuff looks like sugar. All right, don't be doing that stuff. Okay, don't be tasting things to see what they are. That's a no-no. So 4 are the senses. So every lab that we do, you're going to have either one or the other, or most often both of them. There's one lab that I give you that's pure qualitative. It doesn't matter how much we add, how much we're not measuring anything. We're just putting stuff together. That's a pure qualitative lab. Okay, outside of that, most every other lab is quantitative and qualitative. You got to have both. Okay. Again, don't take it for granted. So right from the get-go, when you have to measure something, you should be looking at color and texture and all that kind of stuff from the get-go. Not only are you recording what you're working with, but who you're working with in the process. So if you're filtering something and your filter rate becomes cloudy, that is an observation. Okay. Now I will tell you that with the labs that we do, you need to be within a 5% error. If you're outside of that 5% error, you get docked points. Okay, and I understand that labs don't always go well. So for me, if you're outside of that 5% error, you can get those points back if you can explain why the error was so high. Most of the time, the explanation is going to come from the qualitative data. Okay, so if Carter and I have a 50% error because in step 5 we dropped something, we lost mass because we dropped and we spilled something, that's an easy explanation of what's happening. Okay. However, if it's not in your data, you can't just make it up in the explanation. Well, I think we spilled something. Well, I think this happened. That doesn't work. If you don't record your data real time, you can't go back later and think, yeah, I think that happened. You cannot do that because after lab was over, everything gets very fuzzy and the accuracy of what you observed is not there anymore. So when you're in the moment in the lab, make sure that you're detailed at that time. Okay, you may or may not need the information because you may have a great lab when you're done, but you don't know until you're done. Okay. Okay. Questions on the 2 types of data? All right. Very good. Okay. So today then we're going to take this information we just talked about and you're going to apply it to an activity. And the activity concept is applied to the atomic mass. Okay. My sister-in-law works for NASA. She's an atmospheric chemist, which is really, really cool. And she sent me samples of a new element that was discovered. And the new element has a symbol of capital B, a little n. You want to write some of this stuff down. Okay. So she works for NASA. She developed a computer program that since satellites have a sensor to it for anything that in the atmosphere that shouldn't be there. So if we have chemical warfare from North Korea, okay, her satellites are able to sense anything that shouldn't be in the atmosphere far enough away that we have time to respond to it. Isn't that cool? Yeah, she's pretty smart. Again, she works for NASA. So she sent me samples of this new element with its initials BN. Okay? And she thought it'd be kind of cool if you guys would calculate its atomic mass. Okay, so this is your objective of the activity that you're going to work on today. Your objective is to calculate its atomic mass. And remember, every element has at least 2 isotopes. Okay, so you have to kind of consider that a little bit. Okay? You're going to give me data, both quantitative and qualitative. Okay, so you and your partner have to decide on what data you're going to record. For me, anything that I work with, I'm going to record. I may not need it, but I'm going to write down everything that I measure, everything that I observe. Okay, so you got to show me all your data. Make a data table. Make a data table for your quantitative data. Your qualitative data can be a bullet point. Okay, you can say qualitative data and make a bullet point with all the observations. And then the big thing here is I need calculations. Okay, I need calculations. The biggest calculation is this. You're going to calculate the atomic mass of Bn. Okay. If there is a value that you need along the way that's not measurable and it's a calculation, you have to show me that calculation. So example, if I have a beaker with a solution in it and I have the mass of a beaker and I have mass of beaker plus my solution, and I want to know the mass of my solution. Can I measure the mass of my solution directly? No. But I can take my data and do a calculation and solve for my mass. Okay, I need to see that calculation. Okay? Please, 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 when you do any lab work and any calculations, label what you are solving for. A lot of times, in your mind, you're throwing a bunch of information and stuff down, and you're doing it right, but nothing's labeled. So when I get it, I have to spend time trying to figure out what in the world that you're trying to figure out. In your mind, it makes sense because you're in the moment. Okay? And when I get it, I'm not in your head in a moment, so I got to try to figure out where things are and that sort of, and it gets very, very frustrating. So please, you write out. So maybe you put mass of solution, and then show me the math. Maybe you put percent of this isotope, show me the math. Does that make sense? Okay, so you have all this written down, right? Because this is all one big hoop to do. Okay. All right, here's your sample. This is the new element Bn. And they named this element Beanium is what they named it as. Isn't that cool? This was, actually no, they dug this up. This is something new, something totally new. All right, so this is my analogy of isotopes. Okay, this is not an actual element per se. Okay, my sister-in-law does work for NASA, and she does work for them, and she has created that. That's all true. Okay, but this is from me. Okay, so all these are different types of beans, right? Beans, and so the different types of beans are your isotopes. Is that a good analogy? Yeah, isn't that cool? Oh, cool. Okay, all right. So everybody has their own sample. So when you go to your lab table, you pick a certain side. Your baggie has a number on it. Okay, I know what the answer should be per bag. So please record that number with your data table. Okay, if it's not on there, I'm not going to know where you're at with your math work, and then you get points off. Okay, so make sure that your number of your baggie is recorded. Okay. Also, at your lab table, we have these plastic dishes. They are called a weighing boat because we weigh or mass material. So you can use these as well. Okay, so you have that. You have your baggie here with the different types of isotopes. Okay. Now, one thing that you have to be careful of, we're not measuring AMUs because these are macroscopic, so you're using actual mass for your units, not AMU. Okay. And like all analogies, there's some point in time when the analogy breaks down. I gave you a lot of hints yesterday when we talked through the concept of the atomic mass. Okay. At some point in time, this analogy breaks down. All right. When that happens, you have to figure out how to modify the analogy to make it work to find the atomic mass of your beanium. Okay. For a check system, when you're done, you have a calculation of your atomic mass. The value that you end up with would be something like this. If I took one bean out of here, the mass of that one bean should be plausible. It should make sense. Okay? So whatever you calculate for this, think about it. Does this make sense with taking one bean out of here and measuring it, massing it? If it makes sense, then you're probably on the right track. If it doesn't make sense, then something's a little bit off, and that's where the analogy breaks down. Okay, got it? All right, so you may open the baggie, and you can take the beans and stuff out. Just don't spill the beans. Got that? Okay, there you go. You can take them out, just don't spill the beans, okay? If you happen to have any atoms that you split, if you split some atoms, okay, just be careful. It could be radioactive and you could die. I'm just saying, especially if you swallow it, okay? If you do have some atoms that were split, let me know, so I'll keep track of the baggie and kind of keep it into consideration when I check your math and that sort of thing. Okay? All right, so we have, did we miss anyone today? Lexi today. So we have 29 students. So I can either put you into groups, or are you comfortable with finding your own partner? Give me your thoughts.